Also, the last two chapters that we're going to be going over in lecture are two case studies on two specific operating systems. So we have Linux, which we'll start into today, and then in a few lectures later we'll do Windows, Microsoft Windows. So really, the idea behind these chapters is to take a look at actual operating systems and kind of how they relate to what thus far we've been mostly talking about kind of in a theoretical sense. So when we talk about scheduling, we were talking about the general concept of it. Each operating system chooses to do that particular concept in its own way. Okay. We looked briefly a little bit at how some specific operating systems do some of the tasks. Like we saw a little bit about scheduling in Solaris, scheduling in Windows. Okay, so take a look at Linux. A little bit behind, Linux actually has a fairly interesting history as far as how it came about and kind of the development methodology that it uses compared to other more commercial operating systems. Okay, we'll take a look at that, and then we'll take a look at a few of the concepts that we should be familiar with, like scheduling, process management, and memory management. We will not look quite as much as at the topics that we didn't go into depth, like file systems was probably the major area of operating systems that we didn't go into. Okay, so let's take a look. Okay, we're going to look briefly when talking about Linux. You really have to also talk briefly about Unix as well. The two have a kind of shared history as far as how Linux came about. And then, like I said, look a little bit at how Linux is developed, because it's somewhat unique among operating systems. And then look at some of the concepts. Okay. First of all, Linux itself is usually referring to the system kernel, which we talked briefly about kernels in the introduction. This is really the core of the operating system and really provides a lot of the services that we've been talking about, where we move away from the hardware a bit. So we try not to work directly with the hardware as an application programmer or as a user. What we instead do is we will write to basically the operating system, which in this case, in this context, is the kernel. You'll send requests to the kernel will turn around and then interact directly with the hardware for you. Okay? And we've discussed kind of some of the pros and cons to this type of approach. The idea that your applications are not tied directly to this hardware. You provide a lot of convenience types of services to the application programmer. And then you also help coordinate kind of allocation of resources so that multiple users, multiple programs can utilize the resources, the hardware, at the same time or in a fair manner. Okay? So, the kernel was developed in 1991 by Linus Torvalds, who I think at the time when he developed it, he was a student. But one of the main things here is that it was kind of developed in response to another learning type of operating system at the time, which was Minix, which you see right here. Okay, this was another type of Unix-like operating system that was popular at the time, but it didn't run on the hardware that Linus had, and it didn't run, and he wanted access to the source code and everything so we could see how everything works. Eventually, the story is that he got frustrated trying to work with that, so just wrote his own. Okay, and what's very interesting about the development of Linux is that it was started by an individual, but then later became a project worked on by a community, so by the public. And this was so it's seen as a collaboration among developers to develop a free operating system. Okay, Linux is highly portable. Okay, until Linux, a lot of operating systems were, especially Unix, were very much not written specifically for hardware. They were still written usually in higher level languages, but for practical for all intents and purposes, it was for one hardware platform. So for example, the Solaris operating system, a Unix variant, mainly just ran on hardware provided by Sun Microsystems. Okay, it was written in C, it was portable, but for more economic and business reasons, it wasn't ported to other platforms. Okay, eventually, Solaris was able to run on things like Intel hardware, but initially it was mostly on Sun hardware. Okay, same for IBM's variant of Linux, AIX. Okay, that typically only ran on IBM hardware. Okay, Linux being open source or kind of shared, the source being available and open to the public, many people work to port it to different platforms. Okay, to translate it for use on other hardware platforms. And today it is highly portable. It runs on a variety of platforms. Okay, kind of comparable to this was also another operating system called BSD. Everybody know what BSD stands for? Berkeley Software Distribution. So it's based on a variant of Unix. Unlike BSD, Linux is not actually a Unix. Okay, Unix is a, I believe, trademark name. So really, only those who were licensed by, at the time, I think it was AT&T, could call their operating system Unix. Okay. However, it does mimic a lot of the facilities that Unix provides. Okay, one of the biggest ones is what's known as POSIX. Okay, this is a set of interfaces, kind of at the operating system level, for providing operating system services so that people can write programs to this interface and be able to run it on anything that implements the POSIX interface. Okay. And I forget what the acronym stands for at this point. I believe the first three are for portable operating system, probably interface of some sort. So it's a portable operating system interface. Okay. Let's see. Okay, so this is kind of related to this idea that the core Linux operating system is original code written by Linus Torvalds and then extended by others, but most of the existing Unix software could be compiled to run on it. Okay, and that's where kind of Linux became Linux kind of got a jump start in becoming a full-blown operating system. In that, after developing the kernel, a lot of the software that surrounds a kernel that we're used to when utilizing a computer system was already written for other Unix variants, so they could quickly be used. So, for example, this includes everything from the compilers that were available to even to other basic services like the shell. Okay, like having a shell that you can interact with to talk to the operating system. Okay, other things like network programs and things like that were all kind of available in this kind of abstractly written way that they were made for Unix, but because most of these services were implemented also in Linux, they could just be recompiled with slight modification to run on Linux. So from this kernel, which is a very, very basic piece of software, which talks, which is that thin layer between a programmer and the hardware, we quickly arrived arrive at an operating system that's usable, you know, in the ways that other Unix variants were being used at the time. Okay, and as such, when people talk about the Linux operating system, you're usually talking not just about the kernel, but also some of the surrounding software. In other words, all the software necessary that you need to install on a machine so that you can start using it. Okay, because putting a kernel on an operating system is all very well and good. You'll have scheduling, you'll have file systems, you'll have all these other services, but no way to interact with them, right? So you could boot your computer into Linux and it wouldn't do anything, but you'd be able to if there was some way to talk to it. Okay, so normally all these other pieces that go around it, like the shell and whatnot, are usually what you refer to when you talk about the Linux operating system. Okay, but it should be noted that those other pieces of software are kind of separate, and they are highly portable. So even if you're not familiar with, for example, BSD, a lot of the tools on BSD are the same tools that are being used on Linux. So if you ever try out, if you're familiar with Linux or other Unix operating systems and you try out another, you'll notice that it's all very similar as far as how you interact with it. Now, we've already seen that even if it seems the same interacting with it, that there can be plenty of very, very detailed, low-level things going on that are different. So, for example, even though your program that you've written in C that you can compile on Linux or you can compile on Solaris might work exactly the same way as far as the inputs and outputs are all correct and whatnot on either platform. But how that program is run can be very different from one operating system to another. So even though it might run the same, the scheduling algorithms might be different, for example. Okay, and we've seen that affects things like performance and response time and things like that. Okay, so that's the thing to keep in mind, is that even though the interfaces, the tools, and a lot of the software is the same, how it is run by the kernel can be different. Okay. So, and we see an early version in 1991. This is actually it's running on x86 hardware, very specific file system that it supports, limited device driver support. And I'm sure if we looked at what devices, because again, this is the kernel, so we're responsible for creating the interface between programs and hardware like devices like input, output, and whatnot. Okay, so I'm sure if we looked at what devices were supported, this would be the same list of devices that Linus Torvalds had on his computer, because he was writing this so that he could use this operating system on his computer. Okay, and then eventually this gets put out on the internet, and people join in and write other device drivers, help develop the kernel and whatnot, and then it goes on. And from there on out, that's basically how Linux was developed. Okay, by version 1.0 in 1994, we have networking, a lot of BSD types of services. This socket programming is for creating network programs. We start getting more device drivers. What seems trivial, the idea of running networking protocols over Ethernet, over a networking card, is now available. We have different file systems being introduced as opposed to the older file system, which was being supported from Linux. Okay, and then some additional hardware like disk driver controllers and whatnot. Okay, so okay, and then by version 1.2, this was the final PC-only Linux kernel, which means that it's branched out into other platforms. Okay, and today it runs on a very large number of platforms. You can run it on PowerPC. You can run it on a lot of IBM's hardware. Now runs Linux. They're a big supporter of Linux. Runs on some Motorola phones. It runs on a lot of routers that you can buy at the, go down to Best Buy and buy a Linksys router, and it will probably be running Linux. Okay. Okay. Then, as it develops, we get to the 2 series of Linux kernels, and we are still currently on 2 series of Linux kernels. So, but one of the first major revisions was moving to the 2 series of Linux kernels. Okay, and I'm just talking about the version number of the kernel. Okay, as they develop software, they'll stamp them with a version number, so you know kind of exactly what facilities are available in the kernel and how you can write your software. Typically, what they try to do is make it so that if the first number, right, between 1 and 2, if that's the same, you should generally be able to compile programs to run on that kernel without modification. So what they'll usually change are enhancements kind of behind the scenes. Like if we change the scheduling algorithm to increase performance, your programs don't need to know about that. So that would be an enhancement behind the scene. But if I change how you call things like the disk driver or open files or anything like that, obviously that's a change that impacts you. So I'd try not to change those interfaces if I'm staying in the same first number, right? It's 2 or 1. Okay. As we go to 2.0, we have a lot more architectures. Multiprocessing begins to be introduced in the 2 series. Okay. Before that, it was still you could still run multiple programs, but what they introduced here is actually running multiple concurrent threads of execution on multiple processors. Okay, this was a big shift, and I don't know if any of you were around for that transition. It broke a lot of software. It broke a lot of things, and the multiprocessor support did not perform very well. But today, it is actually Linux is a very decent multiprocessing operating system. Okay, and we've already seen that a transition to something like this can be very difficult. Okay, we saw when we were talking about processes and synchronization that even some of the very basic primitive operations that we do need to be handled differently depending on whether or not you have more than one processor, right? Does anybody remember one of the big things that we talked about that we concentrated a lot on, whether it was single or multiprocessor? Anybody remember? It had to do with locking. Okay, what type of lock is preferred on a multiprocessor that is not necessarily preferred on a single? What's that? No. What's that? Spin lock, right? A spin lock is actually not very well suited for a single processor environment, but suited for a multiprocessor environment. Okay, and some of the facilities that we could use to implement locking on a single processor environment, right, would not help us in a multiprocessor environment, right? Spin locking, where we loop through something while we're waiting on a multiprocessor. What is an alternative to that we could use on a single processor environment? Right. We could put a process to sleep and have it, and then interrupt to wake it up once whatever it's waiting for is available, right? We can't do that in a multiprocessor environment. So you can imagine that if you're writing an operating system, right, you're writing a kernel like these folks were doing, is you went and wrote your scheduler so that you can handle all the different processes running. You wrote all your locks and semaphores using this sleep technique. If you want to move to multiprocessor, what do you have to do? You have to go back, re-engineer all of that so that you can use techniques like spin locking or some alternate method in order to be able to run that on a multiprocessor environment. Because if you don't do that, when you try to run this in a multiprocessor environment, your locking won't work, your multi-threaded applications won't work, and things will start doing all those bad things we saw with locking. Okay, and that did happen. It was difficult. A lot of programs broke and everything, so it was a rough transition. Okay. Other new features include improved memory management, improved networking performance. Okay. What else we got here? Some of the threading model inside the kernel was done differently, and then also this is mainly not threading like what we do, where we write our own threads to run. This is referring to threads that were happening inside the kernel, because the kernel wants might have multiple things that it needs to do, not at the level of a user, but at the level of interacting with the hardware. So this introduced the ability to use those threads inside the kernel. Okay, and then also standardizing other convenience things like a configuration interface. Okay. What types of things do you think could happen here in improving memory management, improving TCP/IP performance? What kinds of things that we've seen do you think were applied here? Like, for example, memory management. What kinds of things could be changed? What are the areas we've talked about that are related to memory management? I'm not asking you to improve on Linux's memory management. I'm just asking what's related to memory management. Okay, so paging is related to page file. So you mean like virtual memory, right? Okay. So we have things like virtual memory. What else? Page tables. Those are two good ones. What kind of things could you do to, for example, improve performance with a page table? Where are some places that page tables may not perform well? What's that? Demand paging. Okay, so like if we weren't demand paging before, we could implement demand paging, which means what? Only. So the memory that the process needs is only put into physical memory when it's needed. So if I'm loading a large program, I don't load all of the parts of that, all of the code and data into memory. What I do is I wait until I encounter the code by running, and then I load it when I encounter it. Okay. What other things could be changed here? How we store the pages themselves, and we've also seen that there can be multi-level paging available. So you could do things like, if you have a page table which has page entries, and then what would be the other side? You have a page as the index. What's stored in the data, in the table? Frames, right? Okay. If this gets very big, right, it could. Where do we store this page table? In memory, right? If this gets very big, it could start using multiple pages itself, right? It could start taking up a large chunk of memory. Well, what you can do is actually put another level in front of it and kind of do demand paging of the page table, right? You can say, well, you need a particular entry. What I'm going to do is notice that that part of the page table is not in memory, so I'm going to go load that part of the page table so I don't have to have the whole thing in memory. Okay? So that kind of thing, the algorithms on how we replace pages and frames could also be changed to alter performance, right? Like in virtual memory, if you need to bring a page in from disk and put it into memory, what's the decision we have to make? What do I have to do? Okay, if I am encountering a situation where I need a particular memory location. Okay, that memory location isn't in physical memory, it's on disk. Okay, so one thing that could happen is I have a free frame. I'll take that page and I'll load it into the frame. But what's the more common scenario? Well, that's checking the valid or invalid would say that it's not in memory. Okay, so I gave you an uncommon situation, which is I go to get to some memory. I notice that it's invalid. It's on disk and not in physical memory. And I have a free frame, right? So I take the page and I load it into that frame. What's the other scenario? Okay, here's another scenario. I go to look for a particular memory location and I notice that it's valid. That means it's in memory. Okay, that's good too. I go to the frame and look up that memory location. Okay, so that's two scenarios, right? One where it was already in a frame, I could go access it. Another, it wasn't in a frame, but I had a free frame, so I could put it in there. What's the other scenario? It's kind of caching. Let me put it this way. The answer to the question, as far as how you can improve performance, is the same answer as most caching questions. What's that? More cache. Oh, getting more cache? Okay. Well, all right. I'm trying to keep it real basic, and that is, I've mentioned two scenarios, right? I'm the operating system. I'm going to get a memory location. Okay. First of all, there's two choices, right? It could be either in memory already, or it could be on disk, right, and not in memory. Okay, so that's one choice that we need to determine. We do that with the valid, invalid data, right? So if it's in memory, I go access it. If it's not in memory, I need to load it into memory. So one scenario in that case would be I have a free frame. I can put it in. What's the other scenario? What's that? Nope. Swap. What? Swap what? Swap with the one that's not using. Okay. I go to load it from disk, and I notice I have a free frame. So I load it into the frame. Just from those words right there. Take one of the words out, and you'll have the answer to the other scenario. Okay? I go to disk. I have a free frame. I put it in the free frame. What's the other variation of that? Go to disk. I don't have a free frame. That's the other scenario. I do not have a free frame. So, what do I need to decide?
Swaps the one in the frame which is not using or less likely to be using. Swap that one out with the one in.
Okay, so what is the decision I'm making? How do I, what I'm saying is you've said, okay, so I take one out and I put this one in. Well, we know we're going to put that one in, right? We went to go get it. So what question remains unanswered? What's that? Okay, that would be nice if we could get more frames, but we don't have any more.
So we can use the one that's not, we can use the frame to kind of use right now, so we can use that.
Okay, so we're going to go to use a frame that's not in use right now? Well, we know none of them are in use right now because we're actually going to get the frame that's actually necessary. So, which one? That's what I'm asking, okay? The question that you need to answer is which frame to take out, okay? We can't just say you just take one out, okay? Well, you can, okay? You can say just take one out, and then you can just randomly choose one and take it out. How do you think that'll work, performance-wise? It might work okay, but not great. So what are some alternatives?
We're not going to take it like randomly frame. We're going to take the first one in the line or something.
Okay, so we could do something like the one that's, if we were to make it like a queue, like a, right? So we could do like the first in, first out type of algorithm. What's a better algorithm? First in, first out means the frame I'm going to choose to empty is the one that is the oldest. It's the one that was loaded the earliest, right? The one that was first in, the first one I'm going to take out. What's another algorithm? What's that? Okay, so you can do first in, last out. Round robin would be kind of first in, first out. What is the preferred algorithm? And this is where this is going back to why the answer to this question is very much like the answer to the caching questions. Do you see how this is a similar problem to caching? Right? Caching is using fast memory to simulate, to make the slower memory seem faster. How do we do that? We take something from main memory, load it into cache, and then work off the cache. We're doing the same thing here. We're taking something off disk, loading into memory, and working off memory. Right? So, if I were to say, what caching algorithm would you like to use? Which would you like to use? Least recently used, so you say it when I'm saying it. But least recently used is the preferred algorithm in both of these scenarios.
But earlier I said that the one less likely to be used. Like,
okay, that doesn't mean the least recently used. Okay, you were actually coming up with a better algorithm, which is hard to do, right? Least recently used is a very definitive. You take the one that has been accessed, right? That whose last access was the earliest, and that's the one you replace. Okay, least recently used is the better. So the idea here is that if we were writing an operating system like Linux, we had some memory management going on, right? We could start tweaking some of these things like the page replacement algorithms, right? We could start changing how we store page, the page tables and whatnot, okay? So that's what operating system development is all about, is you have a working system, and then you can find these places where you can do enhancements to improve overall performance, okay? So, that's all that one little bullet right there. Okay, so, Let's Linux. Okay, this is relating to the surrounding software around Linux. It uses a lot of tools that were developed in a lot of these software projects, like BSD. A lot of the basic tools that were created for BSD are used on Linux. Okay. Another very big contributor to the software used on Linux is this project, the GNU project. Okay. It's actually a lot of the initial compiler and things were GNU pieces of software. Does anyone know what this project is? GNU? Anyone familiar with it? What's that? Okay. it was actually a predecessor to Linux that was attempting to really do what Linux also wanted to do, which is have a free Unix operating system. Okay? The actual acronym actually stands for, it's a recursive acronym. GNU stands for GNU's Not Unix. Oh, sorry, GNU. Actually, I'll write it, because I think even saying it is not clear. Right? GNU's Not Unix, and that's the acronym, but acronyms also. So the idea was this was supposed to be its own operating system that was free, but it had all the facilities of Unix. Well, they didn't have a kernel. And what happened was Linus Torvalds wrote the Linux kernel and then popped it in with all these other tools, and then he had a full operating system. So he kind of beat him to the punch of getting a kernel in there. Okay? Let's see what else. Okay, and then collaboration over the internet, creating this, and now it's used actually in enterprise systems all over the place. Okay? A lot of the internet is run on either Linux or some of the other ones like the BSD variants. BSD. And it's widely used now. Okay? A lot of websites and things, a lot of very large commercial websites are run on this type of open source software. Okay? A distribution is packaging a kernel and all these tools together, usually into a nice, easily installed package. Okay? Some distributions that are out there, Red Hat is very popular. Another one is Debian. You got Red Hat, which is commercial. Debian, which is a more open one, and then these even have variations under them as far as operating systems. The differences between them are what additional software is included with them, how that software is managed, how it's installed, how it's removed, a lot of how it's configured, like the operating system is configured, varies from distribution to distribution. Okay, so, but at the core of them all, they're all running the basic same kernel, and they all provide the same basic libraries and tools. Okay, so the idea is though, even though the user experience of logging into a system, utilizing like the graphical user interface and that kind of thing might look different from one to another, you should still be able to take software written for Linux in general. You should be able to put it on one of those systems, compile it, and run it. Okay? So, licensing of Linux is actually very interesting. It utilizes, again, something from this project, the GNU project, which is the GPL, which is a licensing scheme. Okay, licensing is basically based around copyright. If you write a piece of software, you own the copyright to that software that you've written. Okay. If you were to give somebody this software and say that they can use it in a certain way, that's usually referred to as licensing the software. So if I give you a piece of software and say, okay, you can compile this on your system and use it, and that's it. Okay, that's my license to you. Okay, so you can take that software, compile it, run it on your system, but you're not allowed to give it to anyone. You're not allowed to, in turn, copy that software and give it to somebody else. Okay, because I didn't let you do that on my license. Okay, The GPL is very unique in that, first of all, it enforces that if I give you software, if you modify the software and give it to someone, you also need to give them the source code. Okay? So we all know the difference between source code and a program, right? The source code is the high-level language. We wrote it in like C or C++. We compile that into machine language, and then we run that binary, right? So the idea here and the kind of trick behind the GPL is that if I give you the binary, I have to give you the source code as well. So the trick is that if you modify code licensed under the GPL, what the license is saying is that you also need to put your modifications under the GPL. Okay? So even though you're contributing to it, you're basing it on this original work that I've told you that the only way you can use my original work is if you also distribute the source code when you give it to someone else. Okay? If you're going to be doing software development, I'd look into this. I'd look into how it works because there's a lot of open source software out there. Okay? And open source is usually the type of software that falls under these types of licenses. As you go forward, like becoming a programmer and things like that, it's becoming more and more common to not reinvent the wheel. Okay? If you need a particular piece of functionality, okay, many companies are turning to looking for existing code, whether it's commercial, you go and buy it from somebody, or open source, where you get it from the internet. Okay, but if you are going to use stuff from the internet, you should be familiar with the licensing because it may tie you into your modifications being used in a particular way. So if you modify some of this GPL software, you need to be aware that you're not allowed to distribute it at that point unless you also distribute the source code. Okay? But it's very powerful. There's a lot of more opportunities for software development, even if you don't have a job in that particular area of developing that kind of software. The amount of free code that's available in the world today is just tremendous, and the amount of commercial grade code that's available is tremendous. Okay, if you're going into programming, even just like 10 years ago, there's not this much good source code out there that you can learn from and extend and develop. Okay, a very good resume builder would be participating in open source development so that you can cite all of that as code that you've contributed. So if you do make major modifications to a popular software package and you go apply for a job, you can say, have you ever heard of this? You probably have. I wrote this piece of it. So it's a very powerful licensing model. Okay. Aside from that, Linux is a multi-user, multitasking operating system with Unix-compatible tools. So one of the only major things that separates Linux from a Unix is the name. Okay, and the fact that it's not licensed as a Unix. Okay, it can't use the trademark name, but for the most part, most of the software that you see that can run on Unix can also be compiled to run on Linux. Okay, and in fact, there's some facilities inside Linux that allow you to directly run some Unix software. Okay, this is a little different from. There's two types of kind of portability. One is if you can take the same binary, bring it to another system and run it. Okay, the more common one in Unix is you can take the same source code from one, bring it to another, and compile it and run it. Okay, if you're more familiar with Mac style, Apple software or Macintosh or Microsoft software, you might not be familiar with the idea of portability using source code because typically you work only with binaries that run directly on the machine and you never get the source code. Okay, Unix style software usually includes source code. Okay. Okay. So here's the just a statement that it's designed to be compliant with POSIX, which means that if you write to this interface, use all of the different system calls of this interface, you should be able to run on anything that has POSIX on it. Okay. Interestingly enough, like Windows, I don't know if they still do, but at one point had a POSIX interface as well. So you could actually port software between Unix and Windows, at least at the fundamental level of these interfaces. What's that? I don't know if they still include it or not. I know they did back like in 4.0 and stuff. I don't know if they've discontinued it though. I'm sure it's still available in some way, but I know at one point it definitely had it, and it may still have it. Okay, because actually, I mean, like Windows has a lot of those types of subsystems. Like a lot of initial software that was being run on it, a lot of it came from older Windows, and older Windows usually runs in a kind of emulated environment inside Windows XP. Like when we transition to Vista, if you're going to upgrade to Vista, most of your XP software will run in kind of a emulated XP environment inside Vista. Okay? A lot of your 32-bit software when going to a 64-bit operating system will kind of run in a kind of emulated environment. Okay? Same thing with this type of thing. POSIX is a subsystem in some of these environments. Okay? Okay, so we have just a little breakdown of the different pieces. The kernel itself is down here, and then we usually put these layers above it so that people can write to those more abstract layers. Because again, this is more hardware oriented down here, but software developers don't want to deal with hardware, right? So they want to deal with very nice, clean programming interfaces. Okay? So we'll usually put a layer of libraries in between the user programs and the kernel. And then above those, we'll write things like compilers, things to manage the rest of the system that's not needed in the kernel. So starting things like web servers and printers and things like that usually run up there. Our other programs, and then utility programs like a shell and directory listing and that kind of thing are another set of tools that kind of run at this higher level. Okay? And what you'll notice about all this is that we have these nice layers so that you could do something like write a basic kernel like Linux, right? And then take all the BSD and GNU tools and run them above it, right? So you don't have to rewrite all that software, okay? So even though all of this stuff was written for commercial Unix, BSD, and other Unix variants, you can directly take them, compile them, and run them on your new kernel, as long as you make your compiler translate those programs into something appropriate for your kernel. Okay. Another introduction of the newer kernels was the idea of loadable modules. This handles things like device drivers. If you had, for example, a particular network card, rather than putting that network card code directly into the kernel, they put it into a module that you could load into the kernel. Right? So you could have the same kernel running with different modules depending on which network card you have plugged in. Right? That made it very portable so that I could run it on my machine, which is running, company A's network card, and you could run the same source, kernel on your machine, which is running company B's network driver. Okay? This was actually a big change because the overall design of Linux is what's called monolithic. Okay? What that means is all of the kernel facilities are written as one big program, compiled all together, and then run on the system. So your disk drivers, your file system drivers, your network card drivers, video drivers, all of those compiled in, run as one piece of software. Okay? This is as opposed to microkernel. Okay, microkernel, the idea is that you have a very, very small core piece of software which is low-level hardware dependent, like your CPU, your memory, and things like that. But even things like network card drivers and all these other pieces are written as separate processes outside the kernel. Okay? There's a difference there in that not putting it into the kernel means that you're very modular. You can.
They are opposite of each other.
Yes. Okay? And Linux is very much in the monolithic camp, and then other operating systems are modern operating systems tended towards microkernel, but there's huge debate as to how much you are one or the other on any of these operating systems. Most of them exhibit both. So, like with loadable modules and things in Linux, it's debatable as to whether that's still considered monolithic or not. Okay, not really, but it acts like it's a microkernel in a lot of ways. Okay, same thing for microkernel operating systems. A lot of those exhibit the same behaviors as monolithic ones. Okay, but it's really just a design approach as to how much code you want to put into that core piece. What do you think the benefit of doing something like monolithic is, as opposed to being modular? Separate it out. Just guess.
Communication will be better because it's in one chunk and their communication,
Right.
internal communication.
Yeah, it's all of that simplified as far as how you talk between pieces like the network driver and that. You're all the same program. You can all talk to each other. Right? You don't have to worry about passing messages or something like that. But that also means that if you screw up talking between modules, you can crash the whole thing, crash the whole kernel. Right? So this is typically, there's debate as to which is faster. Some consider, say that the design of a monolithic type kernel would mean faster because you have less overhead of talking between pieces, right? And then some would say that microkernel development is safer, easier to program, easier to keep bugs out, but that's not necessarily true in either case. So it all boils down to how well you develop your software and how good your software development practices are. Okay. I bet that whole section was horrible for you, yeah? That's all right? All right. Kernel. That. And modules. Okay. So, process managements. This should all be familiar to you, right? The idea of forking and then execing a program inside that. Okay, we saw this in the context of generic Unix when we were talking about fork, but Linux does it the same way as all the other Unix do. Okay, this is going into a little bit more detail that's somewhat interesting as far as when we say that when we created multiple processes, right? We kind of said in a generic fashion, oh, when you create a new process, well, you need to create a new context for it and whatnot, right? So that it can have its own, things like memory and that kind of thing. But we kind of did it in a generic sense of what we need to keep track of for each process. This is getting into a little bit more detail about what Linux specifically does. We have the concept of a process ID, which we've seen with calls like fork and whatnot, right? Like returning a process ID to a parent so that it knows what the child's process ID is, right? Some other things that come in, credentials, okay? This is related to security and protection, right? one of the things that we need to do is that if we are creating a new process, what kind of access and privilege does it have, in relation to its parent? Okay. When we're talking about protection, what are some of the concepts under protection in an operating system that we talked about? What's that? Right. We want to protect resources like data, printers, things like that. What are some of the approaches to that kind of thing? Anybody remember the pictures we drew when talking about protection? Yeah, what's that? Oh, that was in encryption. So protection, though, was before security. We did other pictures for that.
Creating a firewall so that it wouldn't.
Nope. Protection was something a little bit more low level. What's that?
More generic.
It was a little bit more low level. We do pictures. I'll give you pictures involve big circles.
A big circle, like limitation domain.
Domains. There we go. See, I knew the big circles would give it away. Okay, we drew big circles representing domains, right? Inside and to those domains, we assign rights to objects. So, for example, you could have object 1. I can read and write it. I might have object 2, which I can only read. Okay. So what we would say is that a domain has these rights to these objects, right? Okay. So we saw it in the context of things like file permissions, right? We had some domains as the user, another domain as a group, another domain as everyone else. We have read, write, execute, those kinds of permissions, right? Those types of things, those security domains and whatnot, that's what they're talking about here with the idea of credentials, is if I'm spawning a new process, I'm creating a new process, right? And it's going to go off on its own and live its own life as a process on the system. Well, it needs a starting point as to what kind of domains does it have? What kind of access domains does it have, right? What kinds of access to files does it have? What kinds of access to the printers and that kind of thing? Okay, so in Linux, what we do is we will typically associate a child with the user ID and credentials, right? The user ID and rights associated with that user ID of the parent. Okay, and only in particular scenarios do we actually let a child have a different set of credentials than the parent. Okay, one of those very typical scenarios is logging into a system. If you log into a system, we don't want you running with the credentials of the login program, right? I want you to have the credentials of your user. So that's a special program that can create a process and give it a different set of credentials. Okay? Personality that they list here as another feature. This is the idea of having different subsystems that can run programs that are not necessarily for Linux. So it's kind of an emulation system that lets you run binaries from things like, you can emulate a generic way of running Unix programs so that you could, for example, run programs that were compiled for SCO. SCO Unix. That also implements this binary compatibility. So Linux could invoke this personality so that it could run those programs, even though they weren't written for this particular operating system. Okay? Process environment. Okay? This is another thing that's passed on from parent to child. Okay? What is the environment? Well, the environment is just a group of name variables and the value in those variables. Okay? These are not the variables that you put into a program. You know, like when you write a program, you have variables in there. Okay? It's not those. Okay? These are kind of variables outside of your program. Okay? One that comes up a lot in processes on Unix is, for example, path. Right? Is everyone familiar with this variable in their environment? What does path do?
Where to get the directory or something?
Involves directories.
Here, there, to directory.
Right, we'll put directories into the path, so we'll make this equal to different paths. Why would I do that? This is to test to see if you paid attention in systems programming in Unix, which is a prerequisite for this class. Anybody remember what this was for? Okay, I made my path user bin, for example. I mean, what does this mean?
Your root.
No. Everyone has a path. Everyone can have this path if they want. Okay. The path is used to find executables. Okay? When you run a command in a shell or in any program on Unix, right? If I run something like copy, right? The system actually has to find the copy program. So what does it do? Well, it goes through each of the directories that I've listed in my path and looks for a program called copy. So if I type copy file 1 to file 2, if copy is not in this directory, I can't do it. Okay? I'd have to actually tell the system where copy is.
The source code for
No source code involved. No. The program.
yeah. To copy from one file to another, you need a program. So
Yes.
it doesn't think that to get that program. Right? That's what it means. Like when you command line is like copy
CP.
this file, then the other file. So the path.
CP, when you type CP, that is a program. That's a program. So that program, the system needs to know where it is. Okay. The funny thing about Unix and Linux is that, like, if you delete the program ls, you can't do directory listings anymore. Everything that you do in Unix is a program. So this path lets you put all these programs in various places and not have to remember where they are. You just put your path to point to those directories, and it will check for that program in all of those directories. Okay? Otherwise, you have to type in a full absolute path to copy. If I have a program in here that's copy, and I don't have this path, I erase the value in it. Then I can't just do CP anymore. I have to do type all of that out to copy. Okay? So that's one example of a variable that shows up in this environment. Okay? Well, in terms of process creation, what typically happens is when you spawn a new process, it inherits the environment of the parent. So in other words, if you set your path up a certain way, when you spawn new programs, it will also have that path. And so on and so on. Okay? All along the way, though, as we've seen with fork, like the variables that, you know, how they get their own copy, If a child inherits its environment and changes the path, it only changes the path in the child. And then it could have another child and it will have that new set of environment, and then it could change it if it wants. Okay? Okay, and this is interesting in that even you logging into a system follows this behavior. So you'll get a path that you got from kind of the system, right? From the system will give you whatever created the process that is your shell, kind of gave you an environment to run in. But then you can do things like put things in your login script or whatever to change your path so that you have a different path from what the default was. Okay? Typically, when you get into a system, you won't have an empty path. You'll have something in there. And then you can modify it yourself using scripts and things so that you can have a different path. It's very convenient for things like adding in a software package that you use that everyone else doesn't use. Like if you log into Qubit and you want to use Oracle, and there's Oracle on there, you can set your path to point to it, and then you can start using those commands without the system as a whole having to have it set up that way. Okay? So, yeah. That's the environment. It's passed on to children just like some of these other kind of attributes. We got here? Scheduling context. We're familiar with this. Scheduling context. And this up here, the state of a running program. Anybody remember what kind of stuff we talked about there? With scheduling, multiple processes, what kind of stuff? Yeah, we do. Okay, so yeah, some of the different algorithms we use to choose what the next running process is, right? But what do we have to do whenever we switch processes? We have the context switch, which is what? Okay, so we have to save the state. What kind of things are in the state? What's that? Oh yeah. So we can transition from state from run, wait, ready, terminated, that kind of thing. Okay, those are the states that we can get to. But then there's the system state that also needs to be saved when we switch contexts. If I go from program A to program B, right? What kind of things do I need to save? More general. Keep going. That's one of them. What else? The program counter is a register. So all the registers, we need to save those. Okay? And the program counter being one of the most important. We need to save things like what our view of memory is, right? And that kind of thing. Like all of the stuff that we need when running on the CPU, we save all that. Well, yeah, all the logical addressing, right? The mapping of logical addressing to physical addressing to page tables. We need to save all that before we move on. Okay? That's what we're talking about at the top here. We have in the middle accounting information. Okay, this is some additional information that's stored during these context switches, just because Linux very much targets having multiple users and things like that. Some of the accounting types of information would be how long have you been using the CPU and that kind of thing. So that you can kind of have an overall look of how different processes are using the CPU, which users are using the CPU, and that kind of thing. Okay? The file table, another thing that we have to kind of store. All of our open files, open resources, whether they're printers or any of the hardware that we interact with that we have to open and hold open. We need to save all that information. Okay, so we also have I'll point here that Linux uses the same internal representation for processes and threads. Okay? What they mean by that is that all of those things that we were talking about, this state information, they use the same style of tracking that for both processes and threads. Okay? But what's the only difference for them? A thread is simply a new process that has the same address space. Okay? So what they're saying here is that with threading, you don't necessarily have to treat a thread like a full-blown process, right? You don't have to track all of the same things that you do when you do a process. Okay? What they're saying, what they're saying here is that Linux chooses to treat them all the same. The only difference is that a thread is a process that's sharing the memory space with another process. Which makes sense, right? Because that's the biggest difference between the two. And then it makes it so that your process handling is very generic across whether it's a process or a thread. Okay? A distinction is only made when a new thread is created by clone instead of fork. Okay? Fork creates a new process and has its own copy of the entire context. Clone creates a new process with its own identity, but allowed to share the context of the parent. So that's a thread. Okay? What they're saying here is these are just the system calls that are used that are different between processes and threads. Scheduling. Okay? We looked briefly at Linux's scheduling in the scheduling chapter. Okay, we looked at some different styles of doing the queues. Remember the scheduling queues that we looked at? It was kind of detailed, so I mean, I can imagine that a lot of you don't remember the details, but it was that one where you had kind of an allowance for each of the processes, and then every time they ran, they spent some of their allowance, and when they got done spending all their allowance, they got moved over into the other line. And then once everybody got moved over into the line, the I don't have any more money line, right? They all get moved over there. They all get a new allowance, and then they go back. So that kind of queuing system was specific to Linux, and it was one way to implement all the things we wanted to do with process scheduling. Okay?
So they do like round robin or
No, they do exactly that algorithm that we saw right there. And each of them has their own priority and that's kind of determines how much allowance they get. And actually, I don't know what version of Linux that was referring to, that scheduling system, because I know there was a big change. I don't know if it was, I think it was even newer than this, is they had a big change to the scheduling algorithm. One of their big goals was to get to constant time scheduling. Everybody familiar with this? What's that? Oh, big O, right? Of 1. So what does that mean? Right. It's not dependent on the size of the problem, right? Constant time is a scale of growth for an algorithm. So, what do you think constant time scheduling is? On what? What do you think the size of the problem is for scheduling? What's that? How many processes, right? How many processes you're scheduling? So what they wanted to do is get the constant time for no matter how many processes you have. And I think they did it, and I don't know how much better it is. Because if you're a theoretical person, if you're theoretical, big O of 1 is faster than big O of n, if you're theoretical. Okay? If you're practical, neither of these is necessarily faster than the other. Does anybody know why? big O is talking about the asymptotic growth of an algorithm, which means as you approach infinity, this is how it grows. But when you're talking about that, there's usually a constant involved, where if you're not at infinity, okay, there's this amount of time that you multiply this growth factor by for how big your problem is. So the idea is that if you have big O of 1 with a big constant versus big O of n with a small constant, and n is small relative to the constant, this will be fast. But if this is so big, if the constant in front of big O of 1 is so big that it never approaches the size of the n in big O of n, then it'll be faster. Okay? But those are the types of things that they changed in the scheduling, is changing these algorithms, the choosing of the next process to run, right? We saw that there's plenty of ways to do it. You guys have mentioned a few, round robin. We saw this queuing systems. We saw, first come, first serve. There's a lot of different methods that changing that changes how your system performs. It changes factors like response time. It changes factors like, the throughput and that kind of thing. Okay? We also saw that this is so this is a similar, another look at what we saw with the scheduling, when we talked about in the scheduling chapter. This is just saying that there's different numeric priorities for each of them. These lower numbers are higher priority. Okay, they actually get the idea of like more allowance when it comes to scheduling them than these lower ones. Does anyone notice anything strange about the quantums that are used here relative to the priority? Yeah, they do get bigger quantums. So, does anyone have anything to say about that?
Put the lowest one forever behind.
Their allowance system prevents starvation. What you're talking about is starving the process.
Right.
But we've already, that's a separate problem. It's related, but we already saw with the allowance system, everyone gets to eventually run. Might be a long time, but you'll eventually get to run. If someone can tell me something about the larger quantum up here, smaller quantum, somebody can tell me something about that, I'll be very, very impressed. I'll be impressed because you listen. You have heard the answer to this. Okay. Well, we have a large quantum for high priority, small quantum for the low priority, right? What do you think is involved in the answer? Okay, there's only one thing we're talking about here, right? Larger quantum towards the high priority, small quantum towards low priority. What do you think is involved in the answer? Just think about it the other way, right? What if you had smaller quantum for high priority, larger quantum for low priority? Okay? That would be another way to look at these things, right? So, is this the common way to assign quantum to priorities from what we saw in the theoretical part of scheduling? Just guess. Right. If I'm asking you, right, it's probably not the typical way. Okay, so let me give you that. The typical way is to give smaller quantum to the high priority, larger quantum to the low priority. Why is that? What's that? No, I told you that the typical technique is to give high priority tasks smaller quantum. And this is opposite that.
It's not response time.
You can't just say response time. That's not good enough. It is related to response time. But what do you mean by that? By just saying response time? The top one can run fast. So what do you think goes into those high priority ones?
10 milliseconds.
What goes into the high priority processes?
High priority.
Yes, high priority. What is high priority?
Future tasks that are effective response time.
Okay, so you're saying things that need a high response time are usually higher priority. Okay, so why is that?
Why?
Yes, why?
So the user doesn't feel stupid. When they click on something.
How are you accomplishing that? By doing what you're saying, making these things where you want to click and stuff higher priority. How are you accomplishing this? Alleviating the stupid feeling of users by making them higher priority. Because you know what? You're not necessarily doing that with Linux's system. They're doing the opposite. They're making larger quantum for high priority tasks.
Is that a good thing though?
Is it? Huh? You should what?
Okay. If we give something like 200 ms, right?
Uh-huh.
Wouldn't that be a good thing? Like, what if it needs 200 ms?
Any process would love to have 100% of the CPU.
Exactly.
Okay.
So when you have like a window running,
Mm-hmm.
window 1, 100% of the CPU. So when you click on a window, it will respond faster if it had 100% CPU rather than.
And you're saying that I need a large time quantum to do that?
You might. It'd be better to give a large time quantum something that needs fast response time than a small quantum.
No.
Okay.
It's not. I mean, it's not. You know why? Because things that are responding, in other words, interacting a lot, will probably use small time quantum. Okay, they do not need larger time quantum. Okay, because they are going to release the CPU voluntarily while they're not doing anything, while they're waiting for user input, while they're waiting for screen redraws, while they're waiting for all of these things. Okay, you want to give larger time quanta to lower priority background processes. Why?
To give that less overhead.
Less overhead due to what? Context switching, because you give CPU-bound jobs large time quanta so they can run for an extended period of time, and then you will interrupt them because they would like to use more. High priority interactive jobs, you can give them as long a time quanta as you want. They will give it up voluntarily, more than likely. Why? Because they're going to be waiting on user input. They're going to be waiting on disk access. Okay? This larger time quanta to real-time task has to do with real-time and specific. It's so that you can guarantee a particular level of performance when you get into high priority. The idea is that these high priority tasks, though, will not use all of their time quanta. In other words, chances are they'll be using smaller time quanta than the low priority systems, but you have to give them that to guarantee real-time performance.
So what was the answer?
This is opposite of what normally happens. Why is what normally happens giving small quanta to the top, large quanta to the bottom? The reason being, the low priority non-interactive jobs are CPU-bound processes. These are I/O-bound processes. CPU-bound processes, you want to let them run because you're going to interrupt them and take on the overhead of a context switch. High priority interactive processes will voluntarily give up the CPU and use less of the time quanta and let you not take as much over. Okay? So, this is our active array and an expired array idea. This was where you service all the different priorities. They spend their allowance, get moved over here to the expired array. Once that gets full and there's nobody over here, you swap them out. Okay? Using the two lists and jumping back and forth prevents what you are worried about, starvation, where these low priority ones never get a chance to get to the CPU. They eventually will, because no matter how high a priority these top ones are, they'll eventually run out of credit and have to move over here to the expired array. So we'll always get down to the end. But using the multiple queues with different priorities makes it so that we can get our scheduling where we're servicing those high priority ones often and they're giving up the CPU. And when we get to the low priority ones, they can have long runs of CPU and nobody will be too mad at them because they don't run very often. Okay? And we'll stop there.
I got the homework into this, so I'm going to go ahead and submit the rest.
Okay.
So you send us that, right?
Yeah. I'll get caught up on it today. Oh, for your project? What kind of...